All right, folks, welcome back. This is going to be our second video on Unit 4, Section 6 of AP Calculus, approximating values of a function using local linearity and linearization, or for short, local linearity and linearization. In the last video, we talked about what local linearity was and how to build a linearization, and we used linearizations to complete a couple of examples. Today we're going to add, or in this video, we're going to add another little layer of information related to linearization, and we're going to introduce a topic to you that we're going to talk about more in Unit 5 in order to talk about what we're doing here with these linearizations. So we haven't yet talked about the idea of concavity. Concavity is a very effective tool for us to determine whether an approximation found with a linearization is an overestimate or an underestimate. So we're going to briefly talk about the two types of concavity. Curves are either concave up or concave down, usually if they have a concavity. Lines don't have a concavity, for instance, but most other functions have sections, regions where they are concave up or concave down. If a function is concave up, it looks like an upward opening parabola. That's one way to tell. The derivative of it is increasing over an interval, or the second derivative is positive. All of those things come from a curve being concave up. When a curve's concave down, it looks like a downward opening parabola. The derivative, first derivative, is decreasing. Second derivative is negative. So all those things go with a curve that is concave down. Now, suppose I use a linearization to approximate the value of a function for a curve that is concave up. Imagine what the linearization looks like. It looks like this. And so if I am approximating the value of the function at this x value, the approximation when a curve is concave up is going to be an underestimate, because the linearization is always below the curve, near the point of tangency. Similarly, if a curve is concave down, if I do an approximation there, say I want to approximate the function for this x value over here, the linearization is going to give me an overestimate. So whenever a curve is concave up, we have an underestimate when we use a linearization for approximation, and whenever it's concave down, we have an overestimation. All right, let's move on, and we'll do a couple of examples related to linearization and whether the approximations are overestimates or underestimates. All right, example 3. F is concave up. It tells me here that it's concave up on its domain, and f of 6 equals 3 and f prime of 6 equals 5. What is the estimate for f of 5.7 using the linearization at x equals 6? So we've got the point and we've got the slope to write our linearization. The linearization of the function is going to be the y value of the function plus the derivative of the function times the quantity x minus the x coordinate, which is 6. So that's what our linearization looks like. The best estimate for 5.7 using this model, we're going to use L of 5.7. It's going to be 3 plus 5 times 5.7 minus 6, which is 3 plus 5 times negative 0.3. And so we end up with 1.5 as our approximation. Is it an underestimate or an overestimate? Well, since the curve is concave up, the linearization leads to an underestimate. It is an underestimate. Forgot the letter T there. Underestimate because f of x is concave down. Or pardon me, concave up. I'm sorry. My brain short-circuited there for a second. Concave up. Okay, example 4. Part A, for each of the following questions, use the function f of x equals negative 2x cubed plus 5x minus 3. First, find the tangent line of f at x equals 1. So we want to substitute 1 into this function to get the y-coordinate. We also want to find the slope at 1. So we substitute 1 in here. That's negative 2 times 1 plus 5 times 1 minus 3. And it looks like f of 1 is equal to 0. Wow. And then I need the value of the derivative at 1 also. So I find the derivative, f prime of x is negative 6x squared plus 5. So f prime of 1 is equal to negative 6 plus 5, or negative 1. And so now my linearization is going to be, linearization is equal to the or the y-coordinate of the function, which is 0, plus the derivative at 1 times x minus the x-coordinate of the function. And so this is my linearization or tangent line to the curve. Part B, what's the estimate for f of 1.05 using the linearization for f at x equals 1? So we're just going to go ahead and find L of 1.05. It's negative 1 times 1.05 minus 1. And that ends up being negative 0.05 for our estimate for f of 1.05 using this linearization. And then part C, is the estimate from part B an overestimate or an underestimate? Justify your answer. Well, in example 3, we were told that the curve was concave up. Here, we actually have to figure out whether it's concave up or concave down on the interval. And the easiest way to do that is by looking at the second derivative. If the second derivative is positive, it's concave up. If the second derivative is negative, it's concave down. So I'm going to take my original function and take the derivative of that. In fact, I already did in part A. And then I'm going to take my second derivative. And so the second derivative of this function is negative 12x. And so let's see, if I substitute 1 in here, or pardon me, if I substitute 1.05 in here, I get a negative value. I don't even care about the numerical value of it. You know, it's 12.6. Therefore, this curve is concave down. And to answer our question, the estimate from part B is an overestimate since f of x is concave down around this linearization. All right, and we are all finished with this video and this section. Come back next time. We'll talk about information from section 7 of Unit 4. Have a great rest of your day and enjoy yourself. See you again soon.